Okay, so now we're going to be discussing about how to solve higher order constant coefficient differential equations. First, just to establish, solving differential equations generally with an x variable is extremely difficult because it requires some kind of reduction of order and generalizing reduction of order for if there's third order, fourth order, and higher. So it becomes a little too complicated. And in general, we don't have to really solve these kind of systems because they don't really model any kind of physical system that we can really feel for. So as such, we keep it with constant coefficients because we could model RLC networks, for example, with it. First, I want to consider the simplest case, a second order differential equation with constant coefficients. Now, P and Q are constants, any kind of constants. But in order to solve this, we have to turn it into an auxiliary polynomial. An auxiliary polynomial is just some kind of exponential, it's just some kind of polynomial that we turn a differential equation into using the following substitution. Now notice, if we have dy dx, this is just me to the mx, and then d squared y dx squared is just m squared e to the mx. So substituting these in, we get m squared e to the mx plus pm e to the mx plus qe to the mx equals 0. Now, we will factor out e to the mx. We have m squared plus pm plus q equals 0. Now, e to the mx being equal to 0 is only true for when x is negative infinity. But in a physical system, we can't have negative time, or rather, it's not really feasible to have negative time. So as such, we consider this a trivial solution, which allows us to focus on the following. M squared plus pm plus q equals 0. Now, we can express this in the quadratic form, and we're able to solve for both solutions. m1 comma 2 is equal to negative m plus minus the square root of p squared minus 4q divided by 2. Now, because of the discriminant, which is this square root right here, we have three cases. Case 1, suppose that we have m1 not equal to m2, but that p squared minus 4q is greater than 0. We have real distinct solutions, and as such, our complementary solution is c1e to the m1x plus c2e to the m2x, and that would be our solution to the second order differential equation. Case 2. Suppose that we have m1 equal to m2, which just also means that p squared minus 4q is equal to 0. Now, in this situation, we only get one solution, and the solution actually is modeled by this. yc is equal to c1e to the m1x plus c2x e to the m1x. So in order to have two unique solutions, we must have one without x and one with x. Then case 3. Suppose then again that m1 is not equal to m2, but that the solution based on the discriminant is imaginary. So we get some kind of form that is a complex conjugate. We get a plus minus bi, or for fellow engineers, a plus minus bj. Now, it doesn't really matter for the notation. Our complementary solution becomes e to the ax c1 cosine of bx plus c2 sine of bx. And that models a complex but distinct set of solutions, which is modeled by a complex conjugate. Now, just in general, higher order is the same as saying is similar to higher degree in terms of its behavior. Because what this is actually saying is that higher degree is always some kind of number of second degree plus number of first degree. In essence, that we can break down every single kind of third order, fourth order, and higher into a combination of second degree and first degree. What that essentially tells us is that for an auxiliary polynomial, and therefore for a differential equation, we only have 3 cases. And going for third order and higher, we have combinations of those 3 cases. In the next video, we're going to do one problem and show us, and we're going to do a couple of problems just to see these different cases in action. And then we'll finish it off by talking about the applications of second order and higher differential equation. Okay, thank you.